All right, AP Chem, let's look at your multiple choice review number 2, most missed questions. A lot of these have a similar theme, and I'll walk through each one for you. Which of the following arranges the molecules N2, O2, and F2 in order of their bond enthalpies from least to greatest? Bond enthalpies, that's your bond energies. How much energy does it take to break 1 mole of these molecules apart is what the bond enthalpy would be. So let's look at our molecules first by drawing them. So N2, if you draw your Lewis structure for N2, it looks like this. There's 5 valence electrons on each. Oxygen has 6 valence electrons on each, and you end up with a Lewis structure like this. And fluorine has 7 valence electrons on each, and you end up with a single bond Lewis structure. How do I compare the bond enthalpies? Well, the number of electrons that are shared in the middle, or the bond order. This would be first order, second order, third order, which would be triple bond, single bond, and double bond. That's your primary determining factor for the energy required to break it. The triple bond requires more energy to break. It's harder to break this molecule than it is the O2, and then harder for O2 than F2. And that's what makes A correct. Another comment for this, these are all in the same period on your periodic table. So if you look at your periodic table, all of these elements are in period 2 in that second row. So they're all similar sized atoms. So we can assume that the size of the atom's not impacting the energy here very much. They can be relatively close to the same distance apart. And the only thing that's affecting it is your bond order. Another way to think about that, there's 6 negative electrons here being shared. Well, the positive nuclei of each one of these nitrogens can have a much stronger attraction to the 6 negatives and held into this bond than the fluorine can, even though it's a 9 protons, and the nitrogen doesn't have 9 protons, it has 7. The fluorine is only attracted to 2 negatives on the inside. So Coulomb's law says that these 2 nuclei would be stronger attractions towards the bond electrons. Okay, let's take a look at this one. The particulate level diagram of a metallic element is shown above. Typically, metals are both malleable and ductile. That means it can be pounded into a sheet or stretched without breaking. The best explanation for these properties is that the electrons involved in bonding among metal atoms are the reason that I expect that most of you got this wrong is because you didn't understand what directional means. Let's just look at our first part here. It's either unequally shared or equally shared for the bonding. Well, these electrons are free to move all the way throughout this whole structure. That's an equal sharing. An unequal sharing for A and B, unequal sharing would be something like hydrogen attached to fluorine. And fluorine's more electronegative. It gets a negative charge, and the hydrogen gets a positive charge. Electronegativity is what determines how well those negative electrons are attracted to either the hydrogen or the fluorine. They're bonding electrons, how well they get pulled. So fluorine's good at pulling them. That'd be an unequal sharing. Metals don't have unequal sharing. They're equal all the way throughout. So we can get rid of both of those. What does directional mean? Directional means that if we take a compound, let's just take one like this, carbon attached to 4 hydrogens, I can see that there's 4 different bonds, and I can show you the direction of those bonds on this molecule. We would say this is tetrahedral, and there's a 109.5 degree angle between all those bonds. Directional means that they're going to stay that way. The carbon's going to have all those hydrogens in fixed locations around it. For metals, it's non-directional, which means if I grab a cation here, all it cares about is it's participating in the sea of electrons, but I could move this cation or the nuclei of the metal wherever I want to, and that's what it means to be able to hit it and bend it. That'd be non-directional. So we are equal sharing and non-directional. Non-directional would be the same thing as what we would say delocalized when we talked about metals. Okay. Which of the following correctly indicates whether the solid represented by the particulate model shown above conducts electricity or explains why or why not? I moved it down below here. You should readily be able to identify that this is an ionic compound. We have positive ions and negative ions attracted to each other in a crystalline lattice structure. That ionic structure is fixed. These would be directional, and they'd be fixed in one spot. The positive ion's not going to change locations here. If you hit it with a hammer, it would break. It wouldn't bend. So let's look at our choices here. A, it conducts electricity because it's made of positive and negative ions. Tempting choice here because it is positive and negative ions, but it cannot conduct electricity because they can't move. To conduct electricity, you have to have positive and negative charges that can move freely. If you dissolve this in water, the ions would break apart and they would be able to move, and ionic compounds dissolved in water do conduct electricity, but not in the solid state. B, it conducts electricity because it's made of particles of different sizes. Your size of your particles are not going to determine your ability to conduct electricity. C, it does not conduct electricity because its ions cannot move. This is the correct answer. And D, it does not conduct electricity because there are small spaces. Again, your spacing is not going to make a difference for this example. Which of the following statements, if true, would support the claim that NO3- ion represented above has 3 resonance structures? The resonance structures come from this double bond here being able to be located in 3 different spots. And those 3 different spots, it doesn't find one of those locations, it distributes equally across all 3 of those. So we could draw all 3 of those resonance structures, one here and one here. Let's look at C and D first here. One of the bonds is longer than the other 2, or one of the bonds is shorter than the other 2. Both of these, if this was true, would support not having resonance. In other words, if this double bond only exists on one oxygen, that double bonded nitrogen oxygen would be a shorter bond than the single bonded nitrogen oxygen. And if that were the case, we would say that those electrons are fixed in just one spot in our molecule. But if you measure these, they're actually all the same size. And if they're all the same size for the bond lengths, they have to have the same number of electrons between the 2. And so C and D would represent not having a resonance structure, and it's not actually observed in nature. B, the oxygen and nitrogen bond angles are 90. They're actually 120. 3 things attached to any central atom will give 120, so this is incorrect. That leaves us only with A, and let's describe why A is correct here. It's a non-polar species. That would mean that we have equal distribution of electrons all the way across for all oxygens on this in our Lewis structure. And for that to happen, these electrons here have to be equally distributed. The extra 2 electrons here equally distributed among the other 2 oxygens on our structure. Which of the following complete Lewis diagrams represents a molecule containing a bond angle that's closest to 120? You need to remember your geometries here. And your geometries, for all structures where you have a central atom with 3 things attached to it, it could be 3 atoms, or it could be 2 atoms and a lone pair electron site. This would be a lone pair. They're going to have an angle of 120. So that's what we're looking for up here. Are any of these Lewis structures consisting of a central atom with 3 things attached? Well, this one only has 2 things attached. This would be a linear, or 180 for our angle. This has 4 things attached. This would be a 105, a tetrahedral. This has 4 things attached, 3 atoms and 1 lone pair. This would be 109.5, but it'd actually be slightly less than 109.5 because the repulsion of these extra electrons here would repel the bonds of the 3 hydrogens. And D here, this would be 109.5 tetrahedral for this carbon, but this carbon right here, the central one, has only 3 things attached, 1 oxygen, 1 carbon. We don't care that there's a double bond here. The double bond still only occupies 1 location in space when we're talking about geometries of molecules. And an example of that is our carbon dioxide at the top here. Carbon dioxide has double bond on both sides, but this structure looks exactly like this, a straight linear one. So this would just be carbon. If you actually drew this for the geometry, it would look like this. And just a good reminder, we don't draw Lewis structures for geometry. We just draw them to show the location of electrons. You're not going to get your angles from a Lewis structure. You have to look at how many things are attached to each one of the objects in the Lewis structure, or atoms, to be able to determine your geometry. Which of the following Lewis electron dot diagrams represents a molecule that contains the smallest bond angle? Smallest bond angle, we're going to do our little geometry is this good reference table to have here. Let's count how many things we have attached to the central carbon here. 1, 2, 3, 4. This would be 109.5, which would be our tetrahedral arrangement. B, 1, 2, 3, and then 4 is our lone pair electrons. Well, those lone pair electrons will repel. Where are we? Here's our NH3. These lone pair electrons will repel all of these bonds. They'll actually force these to get closer together. And when they get closer together, it reduces those bond angles. So this would be something less than, I'll draw less than 109.5. And then C, we have 3 things attached to it. That's going to be our 120. So this can't be our choice. And then D, we have 3 things attached, 2 atoms and 1 lone pair. That's also going to be 120, but slightly less than 120. And this is not our answer either, and that's what makes B the correct choice. It has the smallest bond angle. Which of the following molecules contains exactly 3 sigma bonds and 2 pi bonds? Let's draw these. Good practice for Lewis structures here. Your carbon has 4 bonding sites. I'll just put those in here. You know that your hydrogen is not going to be able to be a central atom. So carbon attaches to carbon here. And then we have a hydrogen and hydrogen that uses up all of our atoms. To satisfy the octets, this bonding site and this bonding site have to overlap and make a triple bond. So our compound looks like this. And just a refresher for sigma and pi bonds, sigma bonds, this is always your first bond that forms. It's overlap of orbitals. Your pi bond would be a double or a triple bond. Every time you add a bond to a sigma bond, it's a pi bond. So you can only have one sigma bond between two atoms, and then everything after that would have to be a pi. So we have one sigma bond here, and we have between our carbons one sigma bond, the first one, and then between these two, another sigma bond. So we have three sigma bonds here. In the center here, one of those is a sigma bond. The other two are pi bonds. They're the overlap of unhybridized p orbitals. And it kind of just sandwiches the top and bottom and makes a pi bond. So this is our correct answer, 3 sigma and 2 pi. Let's look at our other ones. Carbon dioxide looks like this, an oxygen and an oxygen. Well, your first bond on each of these is a sigma bond. That gives us 2 sigma bonds. And we have 2 pi bonds because we have 2 double bonds there. So this would be a 2 and 2. HCN, you would have to do a formal charges here to figure out which one of these the carbon and nitrogen is in the center, and you could prove that. Let's see if we did that correct. This would be carbon formal charge. If you don't remember how to do that, carbon has 4 valence electrons. Subtract the number of electrons that belong to it in the structure. They only get one of each of the electrons for the bond. So it gets 1, 2, 3, 4. Each bond gives its 1 electron. So the formal charge for carbon here is 0. That's good. Formal charge for hydrogen is 0. You could do the same thing for nitrogen. 5 minus 1, 2. It gets both these electrons. 3, 4, 5. It's 0. And this is the best structure with the carbon in the middle because everything has a formal charge of 0. So let's evaluate our bonds here. 1 sigma, so we get 2 sigma bonds. And we get 2 pi bonds for our triple bond right here, and it's going to be the same as B. For D, I'll let you see if you can draw those, and E, draw that and determine the sigma and pi bonds for those. If you're curious to see if you got the answer correct, just do a quick Google search and you'll find those Lewis structures, and hopefully you can evaluate your sigma and pi bonds there. Our last one here. This problem asks you to identify which one of these is nitrogen, which one's hydrogen, and which one's oxygen on the graph here. To do that, we want to first determine what is this graph measuring. It's measuring the potential energy stored in the bonds between two atoms. Internuclear distance would be how far apart those atoms are. So it's measuring the energy of the bond and the length of the bond. The internuclear distance or length of the bond gets larger as you go to the right on this graph. So if we draw each one of these structures, we're going to be able to predict which one of the lines or curves represents each one of these molecules. So here's our choices for Lewis structures. The first thing you should recognize is we have a single, double, and triple. Now, how do I differentiate between these two? Well, or these three. The triple bond is going to have the highest energy. That's what you want to look at first. Don't try to do length of the bond first. Do the highest energy. These two are pretty close in energy, so it's hard to tell the X2 and the Z2, but the Y is a lot more energy required to break that bond. And we talked on the first question in this session why the triple bond has high energy. So N2 would be our low one here. Then I want to compare, how do I know which one of these two is my hydrogen and oxygen? Well, energy is not going to be your choice here. They're close to the same energy. Let's compare the bond length for these. What would you expect if you compare nitrogen to oxygen? Well, nitrogen and oxygen have the same period on the periodic table, so they're about the same size atom. And if they're the same size atom next to each other, the one with the triple bond is going to be stronger attraction and pull them closer. So nitrogen would be a smaller bond than our oxygen, our double bond. So this has to be oxygen, a little bit larger in nuclear distance. This is our O2. And that leaves H2 being our last one here. And you might be saying, how can H2 be smaller than our N2 and our O2 if it's a single bond? Well, the answer is the hydrogen is one of our smallest atoms on the periodic table. And that really small atom allows, all it is one proton and one electron. It allows those two hydrogens, really small atoms, to get really, really close together. And that distance between the two, there's my little smiley face, is going to be extremely small because your atoms are really small. So that's how you answer that question. I hope that helps. There's your most missed for multiple choice number 2.